40-50 minutes, we're going to describe this experiment in a really qualitative sense. I'm going to spend time on this because this is the essence of quantum mechanics. Richard Feynman said that this experiment is at the heart of quantum mechanics. All there is to be understood about quantum physics is encapsulated in this experiment and its different variants. Alright, so we're spending a good deal of time on this. First of all, you came up with many questions during the break, which is really good. This is an inspiring sign. And I'm going to answer those questions, or I'm going to try to answer those questions one by one. First of all, even a slight commotion disturbs me, unfortunately. Remember, there's only one electron in this system at a time. So how do we see interference patterns when there's only one electron, and that electron impinges and produces a speck of a signal on one point on the screen? What do we mean by interference patterns? We have to run this experiment for a certain length of time. And we see how the pattern builds up over time. Alright? This is what we actually have to do in our experiment. We can't say whether we are seeing an interference fringe or not just by looking at one electron. We have to let the course of the experiment, let the experiment run over its course for an extended period of time. Alright? So that we can decide whether we see fringes or not. Alright? So now this is the outcome of a real experiment that was performed 4 or 5 years ago with electrons. And this is what you observe on a screen. This is the screen that I drew at the right most position. And whenever an electron impinges on a particular point in the screen, you get a bright dot. So this is the outcome of a real experiment performed inside a laboratory. Alright? So let me run this simulation. It's not a simulation, by the way. Let me run this result and see what will happen. Full scale पे शायद में अच्छा नजर ना आए. Full scale. Whoa. इसमें नजर नहीं आया है.
सर जूम कर लें.
पीछे से डॉट्स नजर आ रहे हैं?
यस. नहीं
थोड़ा से जाना.
कंट्रोल नजर आ रहा है? So each speck on this screen is representing a single electron falling on the screen. So we're detecting single electrons one by one. And there's only one electron through the apparatus at a given point in time. All right. Alright, now there are many questions that need to be asked and need to be answered. So just give me 5 or 10 minutes to describe what I have in my mind so that I can field more questions. Alright? The first observation is, what do we mean by detection? Now these electrons are, of course, they are microscopic particles, they are subatomic particles, but how do we observe electrons? We observe electrons by some macroscopic device, some big device that we are accustomed to, because we have to make an observation. Without observation and without measurement, there is no physics. So if we were to say that we would like to test the results of or the outcomes of quantum theory, we have to perform experiments. In this case, we have to detect where do electrons land, where do electrons fall, where do electrons reach, which slit the electron goes through. So we have to answer these questions. For that we need detectors. The screen over there is one kind of detector. It's a big screen, right? Millimeter size, centimeter size. Definitely it's not the size of an electron. It could be a photodiode. The electron is a minute particle, but the photodiode is big. It has electrodes associated with it. It has a power supply associated with it. A loudspeaker which gives a click on an electron, or on the falling of an electron, is a big device. You've used Geiger-Müller tubes in the lab. These are big devices that detect nuclear particles. So you need some kind of detection device. And one kind of detection device is a screen. That's a detection device. A camera is a detection device. Here the light bulb is being used as a detection device. If we were to look at the reporter or the spy, the light bulb is being used as a detection device because it's throwing off photons or light, and those photons are bouncing off from the surface of an electron and reaching our eye. Alright? So the light bulb is being used as a measurer, as a measurement device. The human retina is also a measurement device. When you see something, you're making an observation. When you're looking at the sun or the moon, or you're looking at me, you're making an observation. You're detecting my presence. Alright? So the human retina is a measurement device. All of these are macroscopic devices. Now, if you insert a measurement device, which is the light bulb, in the experiment, outcome is totally different than if the light bulb were absent. So the apparatus with the measurement device, with the macroscopic measurement device, is different from the experiment without the measurement device. Which means that the detection or the measurement is affecting the outcome of an experiment. Which is really strange. In classical physics, we would assume that the electron or any particle has an objective reality. Okay? It has an objective reality. It exists whether you observe it or not. And its properties are independent of whether you are able to observe those properties or not. Alright? So there is some objective reality in our classical notion of physics, of how this world works. Quantum mechanics dethrones this objective reality. It just replaces this objective reality and proposes that the measurement device is not exogenous, is not external to the experiment. The measurement device is a part of nature, is a part of the experiment. Having a measurement device in the experiment is going to change the experiment altogether. This means that when we try to interfere in the experiment as observers, as detectors, then we are changing the experiment altogether. A new experiment, a new reality is born. which means there is no such thing as objective reality of an electron. The concept of reality changes. Right? Now there's a new reality. The new reality states that the macroscopic measurement device, the observer, is a part of the experiment. It's not exogenous or external to the experiment. It's a part and parcel of the experiment. It defines the experiment. What kind of properties you will observe for an electron, whether it's a wave or a particle, depends upon the kind of measurement that you do. And where are you performing that measurement? In this experiment, if you didn't perform this observation, you perform this observation upon the screen, you'll get one outcome. If you included the experiment and tried to find out, pry open the black box and see which, and you're trying to be clever and you're trying to find out which path the electron is taking, then the experiment changes altogether. And now the electron is not behaving like a wave, it's behaving like a particle. Alright? So the measurement is affecting the outcome. It altogether radically changes the experiment itself. So there is some element, if you like to use the term, of subjectivity. You look at the experiment in a different way, the outcome changes. Okay? So this is one basic notion of quantum mechanics, that the measurement is affecting the outcome. Alright? Now what is meant by a wave and a particle? If you have a wave, now this is something very, very important. So first of all, I mentioned that the detection process is affecting the outcome. In fact, the detection can be inadvertent. Inadvertent means, I'm using these difficult words because I don't know how to explain it otherwise. Inadvertent means ghair iradi. Not deliberate. For example, it's possible that you have not, as a human being, placed a detection device in the instrument, and there is atmosphere. There are atmospheric particles. There is air inside the system, and those air particles are bouncing off the electrons. So the measurement or the observer can be totally inadvertent. You cannot. It's possible that you haven't deliberately placed an apparatus, but still you're not observing the wave nature. The environment can act as an observer itself, and it can affect the outcome of the experiment. In fact, these experiments are extremely fragile. They are affected by these experimental conditions quite a bit. That's why you can't build quantum computers. This effect is called decoherence as well, by the way. And we'll have a full session on quantum computers, which is not conventionally taken up in a modern physics course. Anyway, so first of all, the detection process disturbs the experiment, and disturbance is not a good word because that is slightly a mean word. So I would like to say that the detection process actually changes the experiment. You have a new experiment altogether. The second point that I would like to make is, I would like to highlight what is meant by a particle and a wave. Once more. The electron is giving you an interference pattern, and from the corollary is that the electron is behaving like a wave, because waves interfere. But when you make an observation, what's happening is the electron is a single bunch of, it's a bunch of energy. And if in this experiment, you look at the screen, there's a speck of light on one point on the screen. In the next experiment, there's a speck of light elsewhere, and you're building up these specks of light. So each speck of light is the same intensity. Each one of them is the same brightness. Correct? Each speck of light is the same brightness, which means that each electron is falling on one point on the screen at a time, and it's acting like a particle. So what's happening is that the electron is a wave inside the apparatus, but when it falls on the screen, all of its energy lumps together, coalesces, gathers up, and impinges upon the screen in one go, in one shot. So after it has been detected on the screen, the electron is now acting like a particle. The electron is a wave here, but the act of observation converts it into a particle, creates a particle out of it. So you have a wave in which we don't know where the electron is inside this apparatus. We don't know it. It's a wave, and if I ask you the question, where is the electron inside this apparatus? You will say, it's everywhere. I don't know. It doesn't have a position. Right? It doesn't have a position. Because only then you will get interference patterns. But once the electron impinges upon the screen in a single shot of an experiment, all of that energy that is spread out in this region is lumped together and is given to the screen, is given to the detector. So the detection process collapses the wave. Okay? So we use this word collapse. A wave is collapsed into a particle. So the act of detection collapses the wave into a particle. Alright? Now I'm ready to take one or two questions. Yes? Speak up so that everyone can listen.
Before the detection happens, the electron is essentially a mass that is a collection of energy that's spread out into it. It's not where the electron is. But then again, if the electron is a particle,
it's not a particle then. You see, the problem is that we have to stop thinking of an electron as a wave or a particle. If you're not doing the experiment, the energy is spread out everywhere and you cannot say it's a particle. Alright? So particles and waves are words that predate quantum mechanics. Particle was called a corpuscle in Newton's theory or Huygens theory. These are corpuscles. So these words predate our notion of quantum mechanics. Inside the apparatus, the electron is everywhere. You can't say the electron doesn't have a position. But once the electron falls on the screen, listen carefully, once the electron falls on the screen and reveals its particulate nature on falling upon the screen, its position becomes clear to you. It does have a definite position. So once the electron falls, for example, here, if the electron falls here, there's a speck of light here, there's a flash here, you can tell, yes, the electron has revealed its position to be this particular value in centimeters or meters. So here the electron harbors a realm of possibilities of position. Inside this apparatus, there is a realm of possibilities. So I would like to use this word, it's a very important word. A wave means a realm of possibilities. So before falling on the screen, the electron harbors or possesses a realm of possibilities of position. You don't know which path the electron is taking. It can take any path whatsoever. And before falling on the screen, you cannot tell what is the position of the electron. What is the x of the electron, the path of the electron. After it has been observed, the position of the electron becomes clear, and you can say that the electron has taken this particular value of x. So before, quantum mechanics says that there is a potentiality. Potentiality means there is a realm of range of possibilities of paths and positions. And after the detection process, that realm of possibilities collapses onto one point. Okay? So this kind of reasoning is also called the Copenhagen interpretation. Alright? So these are two important points. So Now let's look at another variant of this experiment so that I can explain this experiment from a different angle. Suppose I have a telescope. Now I perform this experiment once again with single electrons. One electron at a time. And this telescope is aiming at one of the slits, say S3. So instead of a light bulb, I'm now using a telescope that can see an electron. Alright? And this telescope is connected to a switch that is a binary switch. Can be on, can be off. Alright? Now the beauty of this experiment is that if the telescope is off, you're not observing, which means you're not observing the path of the electron. You're not trying to be clever and finding out what the path of the electron is. Alright? Then you let the experiment run for a certain period of time, you will observe fringes. Now the moment you turn on the telescope, you start observing and you run the experiment for a certain period of time, these fringes disappear and you get the bimodal distribution. You turn it on again, the interference pattern reappears. Because this electron, this telescope that is focused on S3, if it gives a flash, it tells you that the electron has passed through S3. It gives you information about the path. Then you don't see interference pattern. If it doesn't give a flash, it still gives you information about the path. Because then you can tell that the electron has gone through the other slit. So the mere presence of this observing device focused on one of the slits is also deciding whether you have interference or no interference. How the electron is behaving. Well, the electron is merely, you can't say that the electron changes its behavior because of the observing device. The electron is still an electron, but the outcome that you see from this experiment depends upon whether you have intruded this apparatus with an observing device or not. Remember that this is also an observation device, but here the observation device is right before the final measurement. It is trying to intrude into the plane where interference is taking place. So how does quantum mechanics come up with an interpretation of all of this? Right? So you can choose whether you want to see interference or no interference just by switching on and off the telescope. Totally strange. So what's happening? How does quantum mechanics describe this? It says that even a single electron we stop thinking of electron as a wave or a particle. It's a field or a quantum field. So when the electron enters this part of the apparatus, it's a field and it's denoted by, say, psi. Generally, this field can also be called a wave function. It's denoted generally by the letter psi. It's a Greek alphabet psi. Psi with a feeble sound of P, psi. Now this electron is everywhere here. Alright? and you stop thinking of the electron as a wave or a particle. It is a field. And you can never ask the question, where is the electron? Because the electron is everywhere. Har jagah hai. Alright? So the electron is everywhere. In poetry, this kind of, for such a person, we call har jai. वो हर जगह फैला हुआ है. So the electron is a har jai. Har jai है. वो हर जगह फैला हुआ है, उसकी कोई जगह नहीं है. हाँ, जब आप उसको देखने की कोशिश करते हैं, तो वो एक जगह सुकड़ के आ जाता है और पार्टिकल बन जाता है. That's what physics is all about. Now, when you pass the electron in this region, where is the electron? It's everywhere. So, listen please. So, what you can say that there is a field associated with the electron with this path, and there is a field associated with the electron taking this path. And the field of the electron inside this region is a superposition. Superposition. It's a sum of both of these components. Alright? So it's a superposition inside this region. Alright? And when you try to make an observation with the telescope, you collapse this superposition. Alright? And you either observe psi 1 or psi 2. If you make an observation here with this telescope, you don't see the superposition. It collapses into either psi 1 or psi 2. And you can tell the path of the electron, but you can't see the interference pattern. If you don't observe here, you turn this off, only then will you be able to see an interference fringe. Yes?
क्यों collapse करती है?
You see, there's a quantum world. But we are classical beings. We have to make measurement. We have to observe and experiment. We have to observe the quantum world. When we make a measurement, we are actually going from the quantum regime to the classical regime. There's a boundary between the two. So, what's the mathematics of this collapse? No one knows. That's why I use the word Copenhagen interpretation. It's an interpretation. ये हमारा ख्याल है कि ऐसे हो रहा है. There is another interpretation called the many worlds interpretation. Now the many worlds interpretation is, let me finish. So the Copenhagen interpretation, if there's a flash of light here, it means that the wave function has collapsed into either psi 1 or psi 2, right? If there's a flash or there is no flash, you can tell which path the electron has taken. Alright? Now the other interpretation is the many worlds interpretation, which states, now don't ask me for the proof of this because no one can prove or disprove it. The other interpretation is that if the telescope sees a flash, then another universe is created. Another world is created in which everything is similar, but the telescope doesn't see a flash in that universe. A new world is created. Alright? So with every experimental outcome, many worlds are created, many possibilities are created. You see a flash in your universe, but in your alternate universe, in the other universe, in the parallel universe, the observer will not see a flash. So both possibilities are created, and you happen to lie in one. Detection की time create होगी. Well, this is a popular theory in classical Sufism as well. It's called occasionalism. Very similar. Anyway, so now what we're seeing here is, look, just a minute please, just a minute. I know there are questions, but let me finish. First of all, the detection or the measurement creates another environmental scenario. It creates a new experiment. There is collapse of the field into a particle upon observation. And the third thing I would like to highlight is the which path information right? So if you have the which path information of the electron, you don't see the interference pattern. So the which path information and interference, they are mutually exclusive. They are mutually exclusive. Mutually exclusive means that if you obtain which path information, you will not obtain an interference pattern. If you obtain an interference pattern, you will not obtain the which path information. Okay? Now, from wave theory, from Young's double-slit experiment, when you see an interference pattern, it means that the interfering waves have a particular wavelength. Correct? Okay, now a little bit of math, just to change the flavor. Alright, according to wave theory, classical physics, now this is very important because this will set the stage for a lot of mathematical investigation that revolves around this kind of idea. So there are two sides, S2 and S3. And you would like to see what's the intensity over here. Now you have a wave coming from this slit and you have a wave coming from this slit. Okay? Now let's call this distance so it's coming from the same source. So this is this arrangement over here. This thing. I'm drawing this thing. So now you have a wave emerging from this slit reaches here and a wave emerging from this slit reaches here. Now you would like to find out whether they constructively interfere here or destructively interfere here. Now this length over here is the same as this length if this were to be a normal. So the difference in path between these rays is just given by this. Correct? Now if this point is at an angle theta with respect to the central axis, and if this distance is small as compared to this large distance, then this angle theta is going to be almost the same as this angle. By geometry. This is something you have to do on your own. But this is the geometry of the problem. Now I would like to find out what's the difference in path between these rays. If this length over here is the same as this length because this is an angle of 90 degrees, then this is going to be the path difference, this much. Now how do I find this path difference? I look at this triangle. This is an angle of 90 degrees. This distance is d. So what is this length? It's d sine of theta. this distance is d sine theta. Now we know that for a wave, ei kx, I'm ignoring the time here. This is a wave. I'm ignoring the time. Time is equal to 0. There could be some phase here as well. Now, if you look at the distance, this is kx is the phase. What we are interested in knowing is what's the phase difference between this ray and this ray. So for that we need to know what's the difference in distance between these rays. And that distance is d sine theta. If I want to find the phase difference, what do I do to a distance? I multiply the distance with k. So the phase difference between this ray y1 and the ray y2 is k times d sine theta. Correct? So this is the difference in phase phi between y1 and y2. Alright? Now this is 2 pi over lambda d sine theta. Now if this phase difference is equal to 0, you get constructive interference. Or if it's equal to 2 pi, you get constructive interference. Or 4 pi, 6 pi, 8 pi, you get constructive interference and you get bright fringes. Alright? And if now this is fixed, d is fixed, you change theta. When you change theta, which means you're going on different points on this screen, you're actually governing whether you're seeing constructive interference or destructive interference. And it depends upon the wavelength as well. Smaller the wavelength, larger will be the separation between the bright and the dark fringes. Now, the phase difference when it's pi or 3 pi or 5 pi, 7 pi, you get destructive interference. Alright? So this is the underlying mathematics of fringes. Now the question is the following. I will see interference pattern only when this lambda is fixed. For a precise lambda, if I have two light sources with changing wavelengths or with different wavelengths, I will not see an interference pattern. I will just see a diffuse smear of light. In order to see interference, my d has to be fixed and my lambda has to be fixed. It has to have a precise value. But what is lambda? Is it related to the momentum? Yes, because lambda is just h over p. So this 2 pi over lambda becomes 2 pi p over h, Planck's constant, d sine theta. So in order to see fringes, you need to have a precise momentum. Right? Precise wavelength means a precise momentum because of the de Broglie relationship. Now if you want to see fringes, you can never obtain which path information. If you have which path information, you don't have fringes. This means that if you find out the position, you cannot find the momentum. The momentum becomes uncertain. And if you find the momentum, if you have a precise knowledge of the momentum, then the position becomes uncertain. Now the position and momentum are like a seesaw. One goes down, the uncertainty in momentum goes down. You know the momentum because you're seeing fringes. You don't know what the position of the electron is. The path becomes smeared out, imprecise. If you know the path, the position, if you know the path or the position, the momentum becomes smeared out. So momentum and position, they are conjugate variables. You know one, if you know the information about the path, you don't know what the momentum is, and the information pattern disappears, and vice versa. So there is what is called an uncertainty relationship, or Heisenberg's uncertainty relationship between position and momentum, and that goes by the following: delta x, delta p, they are greater than a minimum value h bar over 2. This is Heisenberg's uncertainty, and we'll have more to say about this in the next week. So the next week will be devoted to uncertainty principle. Thank you very much.